Welcome to Learning with Philemon. In this video, we will be looking at the orbitals electrons occupy. In the electronic structure video, we saw that electrons occupy specific energy levels. However, contrary to what is shown in the simplified model on the right, electrons in the same energy level do not all occupy a ring as depicted. Electrons actually occupy specific atomic orbitals. In 1926, Erwin Schrödinger, an Austrian physicist, which you may be familiar with from the thought experiment called Schrödinger's cat, demonstrated that electrons in a hydrogen atom can be described by a mathematical wave function. This wave function describes the region of space where there is a high probability of finding an electron. This probability actually differs depending on the distance of the electron from the nucleus, but this is beyond the IB and A-level courses. If you are interested in looking at the mathematics behind these wave functions and at quantum numbers, check out the link in the description. As can be seen in the table, each energy level has different orbitals available that the electron can occupy. In the first energy level, electrons occupy s orbitals. In the second energy level, electrons can occupy s and p orbitals. In the third energy level, electrons can occupy s, p, and d orbitals. But what do these orbitals look like? S orbitals are spherical in shape, but of course the diagram is drawn in 2 dimensions as a circle. The difference between an s orbital in the first energy level, called 1s, and in the second energy level, 2s, is that the 2s orbital will be bigger in size. So the electron in the 2s orbital is more likely to be further from the nucleus, which would be in the center of the orbital, depicted here with a small black dot. Note that these orbitals are not drawn to scale. P orbitals have a figure 8 shape, sometimes called a dumbbell shape. There are 3 different p orbitals. The 2 lobes of the px orbital lie on the x-axis. Note that between the lobes we have the nucleus. This is considered a node, where the probability of finding an electron is 0. The electron cannot be in the nucleus. Similarly, py lies on the y-axis, and pz lies on the z-axis. There are 5 different d orbitals. 4 of the 5 have a daisy-like shape, sometimes referred to as a 4-leaf clover. They can be thought of as putting 2 p orbitals together. Note that the dxy, dyz, and dxz orbitals lie between the axis rather than on the axis. In the dx squared minus y squared orbital, the lobes are on the y and x axes. The dz squared orbital looks like a p orbital with a donut shape surrounding the center. I'm not known for my drawing skills, so it would be better to look at the orbitals in 3 dimensions, using the simulation created by Wolfram Demonstrations project. This can be downloaded for free. Check out the link in the description. Here you can see that in fact the 1s orbital is a sphere. Checking the 2p orbital, we can see that the lobes are on the axis and that we have a node in the middle where the nucleus is. Checking out the 3dx squared minus y squared orbital, we see that the 4 lobes are on the axis. You can also discover the shape of the f orbitals, which is beyond the IB and A-level courses. As you can see, these orbitals are quite complex. According to Pauli's exclusion principle, no 2 electrons can have the same 4 electronic quantum numbers. 2 electrons in the same orbital have 3 quantum numbers that are the same. The 4th quantum number differs. The electrons have opposite spins. Since only 2 spin states are possible, spin up plus a half and spin down minus a half, only 2 electrons can occupy the same orbital. If 3 electrons were present, then the 3rd electron would have the same 4 quantum numbers as another electron. What does all of this tell us about the number of electrons in different energy levels? In the first energy level, you only have an s orbital, so only 2 electrons. Remember that in the GCSE model, the maximum number of electrons in the first energy level was 2. In the second energy level, you have 2 electrons in the s orbital and 6 electrons in the p orbitals, as you have 3 different p orbitals. This makes a total of 8 electrons. Again, this matches the GCSE model. In the third energy level, you have 8 electrons in the s and p orbitals, but also 10 electrons in the d orbitals, as you have 5 different d orbitals. This makes a total of 18 electrons. Here, the simplified atomic model fails, as the d orbitals are not considered. Note that this model does work for elements up to calcium, Ca, as d orbitals are not occupied. Watch the next video, Electron Configuration, to learn which orbitals electrons occupy for specific elements. If you want to dig deeper into the quantum world, check out the link in the description. Thank you for listening. If you haven't already, please subscribe for more content. Stay curious.